All right, let's jump right into this explainer because today we're unpacking a massive breakthrough that is literally rewiring how artificial intelligence processes huge amounts of information. We're looking at a brand new architecture called Kimi Linear. Now, if you've been following AI development, you know that making these models smarter, that's really only half the battle. Making them efficient enough to actually run complex real-time tasks without burning a hole in your pocket is the real frontier. So we're going to explore how a team of researchers just cracked a fundamental memory bottleneck and how this paves the way for a future where AI can instantly recall details from millions of words without crashing your hardware. So, you know how AI sometimes just seems to struggle or slow to a crawl or completely lose the plot when you give it way too much to read at once? Think about it like trying to read a massive, sprawling book, but you have to carry every single page in your hands at the exact same time. The further you read, the heavier that stack gets until eventually you just drop the whole thing. That is exactly the exhausting quadratic memory bottleneck that standard large language models face today. In technical terms, standard attention relies on a linearly growing KV cache. So the more tokens it processes, the more massive that computational overhead gets. It cripples throughput and makes real-time interactivity super difficult. It's really interesting to contrast the two main approaches here. On one side, you've got the heavyweight champion, standard attention. It's incredibly accurate, great at complex reasoning, but man, is it slow and memory hungry. On the other side is the historical underdog, linear attention. Linear attention is built differently. It operates with a constant, highly efficient memory cache. It doesn't hold on to every single page. It's designed for pure speed. But the trade-off? Historically, it's been notoriously forgetful, and it just hasn't been able to match the intelligence of standard attention, especially when you give it long sequences. Well, that brings us to Kimi Linear, which is a totally revolutionary hybrid architecture. It's not just some minor incremental update. It's actually a drop-in replacement for full attention architectures that manages to deliver superior performance and efficiency. It is completely changing the game for tasks that require massive input and output links.
Section 1. The linear attention underdog and why it failed before.
To really appreciate Kimi Linear's victory here, we kind of have to look at the past. See, early linear attention tried to fix that memory bottleneck by taking that giant book we talked about and compressing it into a tiny, fixed-size summary. But because of its finite state capacity, it ended up just forgetting the most crucial details needed for long context retrieval. It lacked that expressivity of standard attention. It's exactly like a student trying to cram an entire textbook into a one-paragraph summary. When the test asks for a really specific detail from chapter 4, yeah, that information is just gone. And that made in-context retrieval really, really tough for pure linear structures. Which brings us to section 2. Enter Kimi Delta, the ultimate solution. The ultimate fix to this whole amnesia problem is something called Kimi Delta Attention, or KDA. Imagine that same student, but now they've got this brilliant, highly advanced smart highlighter. They know exactly which specific facts to hold on to and which to forget, instead of just randomly dumping everything from their brain. KDA pulls this off by using a fine-grained, channel-wise gating mechanism. So rather than a generic forget rate for everything, each individual feature dimension gets its own independent forgetting rate. This incredibly precise regulation means it can selectively grab the critical needles in the haystack while safely tossing out all the useless hay. So how in the world does this run without melting your GPU? By completely streamlining the math. KDA uses a specialized matrix variant called a diagonal plus low rank, or DPLR. Normally, diving into this level of detail creates huge numerical bottlenecks, but KDA smartly binds variables to completely bypass that issue. The result? It actually cuts matrix computations in half and eliminates a few others altogether. This custom algorithm practically doubles operator efficiency and perfectly utilizes hardware tensor cores. Honestly, it's just mathematical elegance translating directly into raw speed. Moving to section 3, a powerful hybrid design teaming up with standard attention. Here is the real secret sauce of Kimi Linear. It doesn't actually ditch standard attention entirely. It teams up with it. They found an optimal 3-to-1 layer-wise hybrid approach. After rigorous testing, researchers realized that stringing together 3 blazing fast KDA layers to handle the bulk of the work, followed by exactly 1 full multi-headlight and attention layer, gives you the absolute best quality to throughput trade-off. It's kind of like having 3 lightning-fast speed readers burning through documents and then reporting back to 1 master synthesizer who preserves the big picture and the global flow of information. And there's another brilliant architectural twist here. The full attention MLA layers in this hybrid model use something called NOPE, which literally stands for No Position Encoding. Standard models almost always use explicit positional encodings to figure out the order of words. But by deliberately stripping that positional encoding out of the full attention layers, Kimi Linear actually forces the fast KDA layers to dynamically capture positional information on their own. That balanced positional bias drastically boosts the model's robustness, making it way better at extrapolating accurately over massive documents than older methods. Section 4. Faster and smarter. Let's look at some really impressive numbers. So, what does this highly technical architecture actually mean in practice? Let's talk throughput. By ditching that massive, constantly growing memory cache of standard attention, Kimi Linear frees up a ton of system resources, which allows for much larger batch sizes. Because of this, Kimi Linear delivers a staggering 6.3 times faster decoding throughput at a 1 million token context length compared to standard attention. Just let that sink in. For a document with 1 million words, it is over 6 times faster. And because it's running on that constant memory KDA mechanism we just talked about, it aggressively slashes KV cache memory usage by up to 75% during long sequence generation. Think about that. You are getting over 6 times the speed while using just a quarter of the memory footprint. This is exactly the kind of massive efficiency leap we need to actually run advanced AI agents affordably in the real world. Now, you might assume that by cutting so much memory out, the AI has to be sacrificing accuracy, right? Well, looking at the benchmarks, the exact opposite is true. Across general knowledge tests like HelloSwag and MMLU, and even tough math pre-training benchmarks like GSM-AK, Kimi Linear just sweeps the board. It outperforms the full attention baseline, it beats out other hybrid models. It proves without a doubt that you do not have to sacrifice intelligence for speed. That fine-grained channel-wise decay really does let it hold on to its most critical reasoning skills. Section 5. The Future of AI Agents, Unlocking Next-Gen Test Time Scaling. This massive reduction in memory overhead, it isn't just a cool party trick. It is the fundamental key to unlocking the next generation of complex reinforcement learning. We see this super clearly on grueling long context evaluations, like the 128K ruler benchmark, which pushes AI to the absolute limit to see if it actually comprehends massive texts. And Kimi Linear is Pareto optimal here. It hits a top score of 84.3, crushing the full attention baseline of 81.3, while running nearly 4 times faster at that length. It's just flat out better and faster. Which brings us to a really exciting frontier. Now that the underdog linear attention has officially leveled up and solved the computation bottleneck of massive AI memory, the whole paradigm shifts. We aren't constrained anymore by an AI forgetting the beginning of a document by the time it gets to the end, or by entire systems crashing from memory overload. With those constraints gone, the only remaining limit on real-time, fluid, highly capable AI agents is our own imagination. Seriously, what incredible tools are you going to build when your AI can effortlessly remember and reason over 1 million tokens in the blink of an eye?